705 In-situ concrete for garden design with John Heather. In-situ concrete is concrete which is fluid when it is placed in position on site. In the last 4 decades, concrete technology has moved on, and the building industry now has a very sophisticated method of specifying and controlling quality. Unfortunately, these systems are for large quantities, and little advice is available for the small contractor who wants to mix a cubic metre or 2 of concrete on site. That technology is still relatively in the dark ages. I will be giving rules of thumb which should produce durable concrete for foundations and pavings. I will mention the use of ferroconcrete for free-form shapes like ponds, and I will talk about trees in relation to wall foundations and pavings. My notes may well seem very cautious at times, but they are based on published industry best practice. My rules of thumb are designed to be robust, to cope with the infrequent storm or the unexpectedly heavy load. Materials which make up concrete are cement, sand and coarse aggregate or stones. You also need clean water of drinking water quality, and sometimes various chemical additives called admixtures are used to retard the setting, impart some frost resistance, increase the workability and to improve waterproof properties. The use of sodium chloride, common table salt, as an antifreeze additive must not be allowed if there is any reinforcement or embedded metal fixings set in the concrete, because calcium chloride accelerates rust. Cement is basically limestone mixed with clay and heated in kilns to a very high temperature and then ground to a fine powder. The manufacture of cement consumes a great deal of energy. There are 7 main types of cement and a number of strength classes for each, making a total of over 30 different specifications. Fortunately for landscape and garden design, you should at most need only 3 types, shown here on the screen. Apart from the normal general purpose cement, there is a cement when you need the concrete to be strong in a matter of days rather than weeks, and also a cement which resists corrosive sulfate salts which occur in some soils. The pre-1991 designation for cements, which are still sometimes used, are also shown in the table. The word Portland is a historic reference to a type of limestone quarried at Portland in Dorset, near Poole on the south coast of England. The local authority building inspector can advise you on the likely presence of sulfates. The degree of sulfate concentration is measured on a scale of 1 to 4. Class 1 is a low sulfate risk. Classes 2 to 4 are progressively higher concentrations of sulfates and may require the specification of sulfate-resistant cement to prevent the attack. Rapid hardening cements gain strength quickly during the first few days, although its final strength is no more than normal cement. It may be useful in allowing light vehicle traffic onto the drives within a few days of laying, or for grouting in cobblestones. Fine and coarse aggregates are the other main constituents of concrete. By definition, fine aggregate is sand with particles less than 5 mm. The sand is sharp sand. The grains are angular, unlike the soft sand used for bricklaying mortar. Coarse aggregate is normally stone with a maximum size of 20 mm. For mass concrete, like deep foundations, it is permissible to use 40 mm maximum size aggregate. At the other end of the scale, it will be easier to bed cobbles into fine concrete, where the maximum size aggregate is 10 mm. If you specify single-sized aggregate, then you will get aggregate where the stones are all very close to the size nominated. If you ask for the maximum sized aggregate, for instance 20 mm, then you will get a graded aggregate with a range of sizes from 20 mm downwards. A well-graded coarse aggregate will have a controlled percentage of each sized particle down to 5 mm. That is the size at which fine aggregate starts. All-in aggregates combine both fine and coarse aggregates in one load. The grading of all-in aggregates is more variable than for nominal-sized aggregates. For small quantities of site-mixed concrete, where the quality is not critical, it may be easier to order all-in aggregate or ballast rather than separate fine and coarse aggregates which then have to be mixed in the correct proportions. Unless otherwise specified, the maximum aggregate size will be 20 mm. The colour and strength of aggregates is unlikely to be of great importance unless they are to be exposed deliberately as part of the surface finishing of the concrete. For instance, granolithic or grano made with hard-wearing granite aggregate. There are 3 ways of mixing concrete: by hand, in a batch mixing machine on site, or ready mixed, obtained from a specialist off-site plant and delivered by mixer lorry. The choice of method will depend largely on the quantity required and any limitations on access to the site. The quality control of ready-mix concrete is excellent if it is supplied under the quality scheme for ready-mix concrete. The control over hand-mixed concrete is least satisfactory. Poorly batched and mixed concrete may not be durable. Durability may be vital in conditions of severe exposure, like a domestic drive, and the surface could crumble within a year or so if it is not durable. In the past, concrete was often specified using nominal proportions. That is to say, the required volumes of cement, sand and coarse aggregate were quoted as a ratio, such as 1 to 2 to 4. This meant in practice that for each shovelful of cement there would be 2 shovelfuls of sand and 4 of coarse aggregate. Unfortunately, a shovelful of wet cohesive sand is very different in volume from a shovelful of dry, free-flowing cement powder. If engineers wanted a guaranteed strength and durability, they had to arrange to take samples of the wet concrete mix, cast it into small cubes, and crush these cubes after 20 days to check on the strength actually achieved. The results were too late to take effective and economically sensible action on small projects. The simple and small-scale use which you as garden designers will normally have for concrete does not usually require sophisticated strength tests. For garden designers, the solution, if high quality is required, is usually to specify ready-mixed concrete. If concrete is being used in sufficient quantity, the use of ready-mix is the best quality control measure and is the obvious choice. Its quality is guaranteed by the supplier in writing. If it is not possible to use ready-mix because of access difficulties or the small amounts required, then reliance has to be placed on a responsible and knowledgeable contractor who will have to work to nominal mix proportions. Access difficulties for the delivery lorries may be overcome by pumping ready-mix concrete from the mixer lorry along 150 mm diameter pipes. Horizontal distances up to 25 meters and vertical distances over obstructions up to 10 meters high are possible even for moderate quantities. Ordering ready-mix is relatively easy. Put simply, you say what you want it for, the supplier does the rest. The term designated mixes is the name given to the quality-assured mixes supplied by ready-mix plants. The table on the screen gives the typical uses and the appropriate reference codes. Ready-mixed concrete has advantages of professional quality control, but the standards to which the ready-mix firm work is geared to the building and the engineering industries, and therefore, in order to specify correctly, you should understand a little of the terminology. Apart from quoting the designated mix reference given in the table, the contractor need only state workability, reinforcement if any, and any special design requirements affecting the way the concrete is to be placed and any method of finishing the surface. The ready-mix supplier then takes full responsibility for the materials and quantities used to meet the requirements, including durability. 20 mm aggregate will be used unless otherwise specified. Site mixed concrete on a domestic scale will inevitably be specified by volume using the nominal proportions in the traditional way. The required minimum quality is achieved by overspecifying the proportion of cement in each mix. The general purpose mix is 1 of cement to 2 of sand to 3 of 20 mm nominal coarse aggregate. Sand changes volume according to its water content. For concrete proportions, it is assumed to be damp. The table in the slide shows typical site mixes and their uses and compares them to the equivalent ready-mix references. For concrete that will be both wet and exposed to frost, like drives and paths, a proprietary air entraining admix should be used to ensure frost resistance and resistance to de-icing salts. This will automatically be included in the designated mixes obtained from ready-mix plants. The admix can be brought from builders' merchants and added to the mixing water strictly in accordance with the manufacturer's instructions. For backfilling of fence posts, use a mix not leaner than 1 to 10 with all in aggregate. Dry lean mix is a term used to refer to a mix of about 1 to 15 or 1 to 18 cement to aggregate proportion, which is mixed with a minimum of water It is used as a base for bitumen macadam and is consolidated by rolling, rather like the use of granular fill. It should only be used with the help of specialist advice. Normal concrete is consolidated by manual tamping, board or mechanical vibrating poker or a vibrating beam. Workability is the word used to describe the ease with which concrete can be spread, levelled and consolidated. Workability can be increased by adding water, but the danger is that too much water leads to a weak, porous concrete. A stiffer mix can be consolidated with mechanical aids, vibrating beams or a vibrating poker. Chemical additives can be used to improve workability with reduced amounts of water. The workability is measured by the slump of fresh concrete and is quoted as a figure, for instance 75 millimeters. In the absence of other instructions, a 75 millimeter slump is the workability which ready-mix plants will supply. Slump represents the amount that a cone-shaped sample of fresh concrete sags under its own weight when it is turned out of its mould. A 10 millimeter slump is a very stiff mix. A 75 millimeter slump is the normal plastic mix. 125 millimeters will give a highly workable mix for applications such as trench fill. The strength, imperviousness and durability of the mature concrete depends to a significant extent on removing the voids either by consolidating the concrete with a mechanical poker vibrator or by hand tamping immediately after placing. These voids to be removed are not the same as those produced by an air-entraining admix to produce minute air bubbles. These microscopic bubbles give improved workability and resistance to frost damage by acting as safety valves for expansion of the ice crystals. Secondly, durability depends on proper curing, which is described in a minute. I will not spend time now discussing formwork for concrete, because this is where a specialist contractor's expertise must be available to help create the effect that you want if the finished concrete is to be exposed to view. Reinforcement is normally mild steel, which is liable to rust. Rust has a greater volume than the original steel, so this expansion eventually causes the concrete to split open or spall. Rusting of reinforcement is controlled by the alkaline nature of new concrete. This alkaline protection slowly disappears over a period of years as the concrete combines with atmospheric carbon dioxide from the surface inwards. Provided the steel has at least 25 millimeters of good quality concrete cover, then a reasonable rust-free life is assured. Therefore, to ensure that the 25 millimeters minimum cover is achieved, the design thickness of the concrete has to be sufficient and the reinforcement has to be secured in place before the concrete is poured to prevent the steel being displaced during pouring. Steel reinforcement comes as bars and welded steel mesh of various diameters and sizes. For example, A142 mesh is sometimes used to control cracking in concrete drives. Ferroconcrete is a mortar reinforced with a fine wire mesh. It is suitable for the construction of small garden free-form ponds up to 3 or 3.5 meters in length. The shape should be a gently shelving side and bottom with no abrupt angles. It should be dug out, and any large stones, roots and rubbish, etc. must be removed before the surface is smoothed and compacted. Use galvanized 20 mm hexagonal wire mesh, folded and cut if necessary, to lie smoothly on the excavation. Tie the cuts and folds securely with galvanized soft iron wire. Then use a 1 to 2 Portland cement to sharp concreting sand to make a cement-rich mortar in a batch mixer. This mix is pressed through the wire so that it surrounds the wire a minimum of 10 mm either side of the mesh. Aim for a 25 mm overall thickness of concrete. Make sure the whole pool is completed in one operation, otherwise there will be a line of weakness in the concrete. The surface is smoothed and compacted by firm troweling using a wooden float. The lining should then be cured immediately under plastic sheeting for 3 days before filling with water. The water must be drained 3 or 4 times at weekly intervals until the alkalinity of the surface cement has decreased enough to permit planting and perhaps for fish to be introduced. Another method of producing thin, crack-free concrete linings for small pools and water canals is to use glass fibre reinforced concrete, known as GRC. Ordinary glass fibre would be corroded by the alkalinity of the cement. Semfil is a product of a French company which produces alkaline-resistant glass fibres specifically for incorporating into concrete. It comes pre-bagged and ready to add to the cement mixer. There is no design guidance available from the manufacturers which is suitable for garden designers. A technical manual is available to engineers, and several firms produce prefabricated rocks, rock faces and cascades or stream beds using GRC. The rule of thumb thickness for concrete slab drives is 100 mm for cars and 150 mm for the occasional use by delivery lorries. For paths taking only foot traffic, 65 to 75 mm thickness is sufficient. A subbase is the name used to describe a consolidated layer of aggregate laid to form a foundation for a drive. The materials used for a subbase are further discussed in the seminar on stone. A subbase is important because it supplies part of the overall strength of the paving. The required thickness of subbase for various soil types is shown on the screen. On heavy clay soils, specify a geotextile layer beneath the subbase to prevent the clay working its way into the subbase should it become wet. The concrete slab should be cast in equal-sized bays, with provision for shrinkage joints round each bay and round any obstruction like drainage manholes. Bay size is to be about 4 meters in both directions. Previous screens show the appropriate mix. For example, PAV1 designated mix automatically includes an air entraining admix for the use on drives. There are various techniques for forming shrinkage and movement joints, for instance by casting the concrete in a checkerboard pattern. This allows the initial shrinkage to take place before the adjacent bay is cast. Alternatively, a deep groove can be cut in the green concrete surface by a abrasive wheel, or a V shape of polythene sheet wrapped under a metal bar can be tamped into the wet concrete to leave the polythene embedded in the surface. These methods encourage the inevitable shrinkage cracks to appear in a controlled rather than a random way. If the drive is more than 60 meters long, there will be a need to form thermal expansion joints right through the concrete slab at 30-meter intervals with 18-millimeter bitumen impregnated fiberboard. Place similar materials between the concrete and any wall or other obstruction against which the slab abuts. For thin 75mm slabs used for footpaths, reduce the distance between shrinkage joints and expansion joints to about 3 meters and 10 meters respectively. Manual compaction of concrete with the edge of a timber board will often leave a slightly ridged finish to the surface of drives. This may be acceptable as a non-slip surface. Alternatively, a smoother sandpaper type finish can be obtained with a wood float or a steel float trowel. A fine textured non-slip finish can be applied to a floated finish by brushing with a stiff broom. Non-slip carborundum granules can be troweled into the surface of steps before the concrete has hardened. Similarly, decorative coarse aggregate can be troweled into the surface and then brushed and washed clean when the concrete has hardened for a few hours. All these finishes need a small trial sample to agree with the contractor and client the effect required. Commercial finishes are available for colouring and imprinting the concrete surface with a range of patterns, as in the screen. The edges of slabs also require special attention to consolidate the concrete into the tight corners and to protect the edges from cracking under load. The appearance can also be improved by giving the edges a slight chamfer or radius in place of the sharp corners or fins. The rule of thumb widths for concrete footings are given in the seminar on walls. Remember to take a specialist advice if, for instance, the ground is clay, which may contain sulfates. The depth of footing to the underside should not be less than 550 millimeters and may need to be considerably more where there is fill or large depths of topsoil. To accommodate sloping ground economically, step footings should change height in modules of brick or block heights. Each step of concrete should be horizontal and should overlap each other by at least twice the change in level, as shown on the screen. Trench fill can give advantages of speed and economy, especially for deep foundations, by keeping the width of trench to a minimum. This is because the trench can be excavated by machine and filled with concrete to near ground level. Therefore, no one is required to work in the trench, either digging or laying bricks, and the trench width needs to be only as wide as structurally necessary to support the wall. Look at the section on the right of the screen. This shows by dotted line the shape of traditional footings. On the left is shown a long section of the overlap of two levels to accommodate sloping ground. Party fence walls are walls built on boundaries with neighbouring properties. Confusingly, it is nothing to do with fences in the usual meaning of the word. If you want to build a wall with its centre line on the boundary, you have to give notice to your neighbour. If the neighbour refuses, your client still has the right to build the face of a wall right up to the boundary and to overlap onto the neighbour's land below ground with unreinforced foundations. You may wish to order the free booklet on Party Wall, etc. Act 1996 from the Office of Public Sector Information. Essentially, the curing of newly poured concrete is to ensure that the cement has sufficient water to complete its chemical hydration process and to avoid damage by frost before the concrete has sufficient strength to resist the ice expansion. Concrete does not set by drying out. Concrete can even set under water, provided the water has not washed out the cement from the mix. Proper curing of concrete will improve both its durability and its strength. In hot weather, concrete should be protected from too rapid drying out by the sun and wind, which will cause shrinkage cracks to develop. In cold weather, the danger is not only frost damage, but also a very slow gain in strength. Concrete should not be poured at or below 2 degrees centigrade, nor should it be poured onto frozen ground or against frozen formwork. The mix should be at 5 degrees centigrade minimum. The temperature can be raised in winter by using hot water in the site mixed concrete or by specifying the required temperature for the ready mix. Concrete itself generates heat as part of its setting process. So if the section of concrete has plenty of bulk and it is covered over soon after pouring, it should suffer no harm from a moderate overnight frost. Proprietary spray-applied curing compounds will seal the surface against hot or windy weather, preventing rapid drying out. But covering in polythene membrane is a more effective and visible in both hot and cold weather. In summer, foot traffic can use concrete drives and paths after 3 days, cars after 10 days, and lorries after 28 days. These times should be increased to 4, 15 and 40 days in cold weather. I now want to summarize. I would like you to remember that there are occasions when your project may need rapid hardening or sulfate-resistant cements. Fine aggregate is sand up to 5 mm sieve size. Concreting sand is sharp and feels gritty. If you are using concrete as a paving, it should be ready mixed if possible and well cured, because paving needs durability. Good curing means protecting from early traffic, keeping it warm and wet for days, preferably under polythene. Large expanses of concrete will need careful design shrinkage joints and expansion joints. The surface can be coloured, imprinted, exposed aggregate, brushed, trowelled, tamped, retarded and pressure washed, even ground smooth and have coloured aggregates scattered on the surface. GRC can be used for lining small water features. The inclusion of fibre reduces cracking and leaks. Trees can be damaged by and can cause damage to concrete foundations, pavings and walls in various ways, particularly on shrinkable clay soils. Primarily, I am concerned in this seminar on the damage trees can do to hard landscape and to buildings. A tree or shrub will sway in high winds, its canopy acting as a huge sail. For that reason, no shrub should be trained against a wall which will exceed 2/3 of the wall's height. This applies to gardens with any type of soil. If its roots or branches are close enough, a tree's movement in a gale can crack footings as the roots move, or push the wall over if the branches come in contact with the top of the wall. The table on the screen shows the British Standard recommended minimum distances when planting a new tree adjacent to an existing or proposed wall. The recommendations depend partly on the size of the trunk you expect the tree to grow to, measured at 1.5 meters above the ground. To avoid all direct damage, a large tree should never be closer than 2 meters from a wall. If it is essential to build a wall close to an existing tree, then space for the roots and branches to grow and move must be allowed. This may necessitate building arches over existing roots or putting in concrete lintels. Movement joints in the wall allow small differential movements to take place in each section of the wall without cracking. You have particular problems if you are building a wall on shrinkable clay or peat soils, and a large tree is either growing or has recently been removed from near the position of the proposed wall. A tree which is growing can remove water, causing subsidence as the clay dries out and shrinks. A tree which has been removed may have left a dry area which will swell or heave as it reabsorbs water over a period of years. This sometimes takes place over as long a period as 3 decades. Either way, the wall and its foundations can become distorted and cracked. Some species of tree remove considerable amounts of water from the subsoil through their root system, and in a dry season this is not replaced. The effect is to dry out the soil. If the trees are growing on shrinkable clay or peat, the drying out over a period of years causes the ground surface to subside. Sometimes this is only the top layers of soil, but the effect of shrinkage can go down to 3 to 5 metres depending on the size and type of tree. Garden designers must be aware of these potentially very expensive effects on both existing and proposed houses and on hard landscape construction. You should therefore check whether the site is in an area of shrinkable clay. This is prevalent in the southeast of England. Consider existing major trees or trees which may have been felled and the future effect they may have on any walls, drives that you are now proposing. Consider the possible damaging effect of planting new trees or large shrubs near proposed or existing houses, drives and walls. Discuss the possible long-term effect with your client and obtain their consent to the risk. Use the table and the rule of thumb on the screen to gauge the safe distance between the problem trees and construction. There is much advice, some of it contradictory, on the safe distance between walls and new trees. As a rule of thumb, on shrinkable clay, the damage to a garden wall will be minimal provided the tree is kept at least half its maximum mature height from the wall, but full mature height from a house. A temporary measure for existing trees may be to reduce the crown by severe pruning by up to 80%, but a vigorous tree will grow back within 3 or 4 years. Tree species at the top of the table have the highest number of reported problems. Trees with no reported problems include magnolias, pines, spruce and yew. If the tree is closer to a garden wall than the rule, or there is a line of trees, then extend the movement joints down right through the concrete footings and consider increasing the number of movement joints recommended in the seminar on the design of walls. To minimize the effect of damage caused by clay shrinkage and heave, the foundations of many modern houses are dug to a considerable depth or even supported on piles. It would be uneconomic to do the same for garden walls. Therefore, it is probable that garden walls will move more than the adjacent house. To ensure that this differential movement does not cause cracking, there should always be an additional movement joint at any junction between a garden wall and a building. I mentioned before that trees can be damaged by pavings and excavations. They can also be damaged by compaction of the soil, pollution, changes in soil level in the root zone, and cutting roots can all kill existing trees. It may not be wise to make even shallow excavations within the root zone of existing mature trees which are to be retained. Where planning permission is needed, local authorities may make special construction techniques mandatory for paving and drainage, etc., in what are known as tree protection zones, TPZs for short. The objective is to avoid damaging roots, preventing compaction of the soil, and to allow water and oxygen to permeate through any construction. Details are shown in the current edition of BS 5837. For instance, using a geogrid fabric, a Type 2 subbase, and a porous block pavers or no fines gravel topping. The area affected should be restricted to 20% of the root zone.